Hello and welcome to the last part of our course on CFD-DEM with OpenHFDIB-DEM. So our last course part will be focused on the CFD-DEM coupling of our library. So basically what we will do is that we just will use the knowledge that we have on general information of our library on how to add individual solid bodies into our computational domain, how some movement modes for the bodies can be prescribed, how to set up discrete element method, and all of this package we will now link to the standard OpenFOAM workflow. So that's our CFD-DEM. So with respect to the workflow, we've covered HFDIB-DEM quite extensively, and now we need to just have a brief look at the standard OpenFOAM approaches. So we will take a look at control dict, FV schemes, FV solution, transport properties, turbulence properties, and so on to put together our case with glitter and impellers. With respect to the code, so we will be using one of the incompressible family solvers that we have, and we actually have only one, Pimple HFDIB foam. And then, code-wise, we will be working with immerse boundary coupling. So in the source library, we have IB interpolation and then OpenHFDIB-DEM, so main object, and immersed body objects. And that's it. And now we have this glitter and impeller. We have this simulation that we would like to reconstruct, but to be honest, due to simulation runtimes, we will be working with only 2D approximation of this. So let's go for the code. So let's open some folder in here, select better screen for code presentation, and that should be it. This we can hide for the time being, and we are in prepared folder in this 00 CFD-DEM. We have folder glitter and impeller 2D. There is glitter and impeller fully 3D, glitter and impeller that is also fully 3D and prepared to run in parallel, but in this course we will work with glitter and impeller 2D. So we will open terminal here, load OpenFOAM 12, and just run all clean and all run before we will start to talk about anything. Just to have some results available. So now the simulation is running, so we can take a look at what actually is running. So as I kind of hinted before, this is just a summary of what we did in the previous parts of the course, and there is some linkage to standard OpenFOAM approaches. So the mesh that we use is the same as for all the glitter and impeller cases. We only decrease the dimension in Z direction because now our Z direction has one cell and is empty. In here. So that's what we did in here in block mesh dict. So we run 2D simulation. In HFDIB-DEM dict, we have our scaled impeller to load in the middle of the domain. We have our glitter. We use the same DEM settings and everything as before, with the difference of geometric directions. We have 2 active geometric directions and 1 inactive. And then, we have glitters acting, so the same LC coef, same rotation model as before. The materials, now we actually use the same material for both, but it's standard material relatively. We have only 4 collision patches because in Z direction we have the empty patches. That's it. Virtual mesh virtual mesh settings, same as before. Impeller scaled with respect to movement. We covered this in a movement modes video. With respect to addition, only once edit, we covered this in body addition. Material is this particle material. With respect to glitters, yeah, it's fully coupled. It has some initial velocity going upwards, but that's just optional. It doesn't need to be settled. Yeah, this raw of the glitters, it's 1000. Here I will just take a brief jump to transport properties for fluid, where we have also fluid density 1000, and the case is actually prepared to be extremely laminar. But so we have fluid density of 1000, we have particle density, fully coupled particles density of 1000, so there is no buoyancy or gravity effect on the particles. Yeah, with respect to boundary conditions, so in here we actually set immersed boundary conditions for velocity in this case, and we have available only no-slip boundary conditions. So this is settings that cannot be updated. Yeah, with respect to body addition model, it's the repeat random position model that we covered in solid body additions, same one. We let it be active over the whole domain, not only some part, but over the whole domain. And we set the target field value of 0.3 because we kind of have a huge impeller in the middle of the domain and we want to have some particles scattered around it. When we put in the particles, same as before, we have these glitters and we scale them to fit inside our domain. And yeah, we have only 2 active directions in our simulation at the moment, so we still have random rotation, but we fix axis for this random rotation. That's this. And there is one more setting, and it's this SD based lambda, where we base the value of our lambda field on the fluid solid interface, not on the volume fraction of occupied cell, because we have this empty direction that does not have any meaning, but we base it on the signed distance from the boundary in STL. But it's just niche settings in here. It works, it gives you better gradient for lambda field when you work in 2D, basically. That's the main reason that we use it in here. And that was the summary of previous videos on setting up the stuff that is special in our library. So now we can go for the standard OpenFOAM things. So boundary conditions for velocity, yeah, there is either empty in empty directions or no slip in all the other directions. Thus, for pressure, we have empty in empty directions and 0 gradient, and we have 2 more fields. We have lambda field for the color function, and in here we set it to be empty in empty directions, 0 gradient everywhere, and this setting can be actually used throughout all your simulations. And similarly, we have the force term, so immersed boundary originating force field, and once more we set it empty at empty directions and 0 gradient on the other boundaries, and this is the universal settings. So these are boundary conditions. Transport properties, we already have been there. In our case, the fluid is Newtonian. It has extremely high kinematic viscosity and density, that of roughly water. Turbulence properties, of course, we work with laminar. With respect to the turbulence simulation in our library, for the time being, we only do direct numerical simulation, so laminar in here. And then standard numerical settings. Control dict, we saw that several times already, but now we have Pimple HFDIB foam solver, so incompressible for solver linked to our library. Yeah, we have some time step and final time times, and this is the same as we used in all the previous videos, basically. But now FV schemes and FV solution is something that we did not have to use up to now, so that's new. For this case, we have fairly dissipative numerics just to have a stable run for show. So temporal derivative is Euler. Here we have linear upwind used, and this is something that I would like to point out, and it's the fact that due to the immerse boundary, it's better to have here fairly stable scheme even for these types of laminar simulations. So we commonly use linear upwind and then some total variation diminishing schemes like min-mod, SFCD or Fanlier in this part. Our mesh is perfectly orthogonal, so it's this setting and that's the whole FV schemes. With respect to FV solution, it's completely standard and the same as you know from all the other simulations in OpenFOAM. So we solve for pressure. It's still our primary variable, so we have settings for pressure solver. We have settings for, this is just our dummy setting for everything, but we actually do not use anything here because we have a momentum predictor turned off. And that's for vast majority of our simulation the suitable setting. So momentum predictor turned off, then we have some outer correctors, inner correctors and non-orthogonal correctors. There are none because we have perfectly orthogonal mesh. And in this case we run it with a consistent simple or pimple variant. Oh, that's it. And the simulation has been running for some time now, so we can take a look at what was happening there. So I will just open ParaView in here, load the simulation results. So it should be here. Let's load it. Hopefully, there is 93 times, so it ran for some time. In here I will just color it by lambda field so you can see what's there. So the impeller as before, now the glitters are not only on the bottom part but kind of scattered throughout the domain. And if we let it run this way, it still adds some glitters because at the beginning here we did not have the target volume fraction, but the add model was not successful in adding the particles, but surely at the end it added all the particles, reached the target solid volume fraction, and now the particles are only moving. So that's one possible view of the domain. There's another, we can color it by current velocity field like this. Of course we can take a look at the force field acting between fluid and solid. It's just dummy field basically. What we can do next is to take a look at the STLs. So it's the same as before. We will take a look at bodies info. Now we are in time 94. Okay, so there is this one, and we will load the STL files. Apply. We have STL files in here. Let's join them. Group dataset. Apply. Different colors. Let's make just slice through this in the Z direction. Crinkle triangulate, doesn't matter. So we have this, color it by velocity, and that's glitter with impellers, and that's it from me basically. So that was the last video of the series. We showed you, I will just go back to this because I have it prepared in here, so why not to use it? And better cut in here. Let's go in here. So in this course we went through the fundamentals of our OpenHFDIB-DEM library. We first presented some general informations. We presented possible ways of body addition into the computational domain, potential movement modes for individual solid bodies. We went through the basics of discrete element method, and in this final video, I hope I was able to briefly outline the full workflow comprising also the OpenFOAM side of the methods. Just final closure for this. All the relevant data for this course and the course materials are, if you are looking on this on YouTube, it's available in the description of this video. If you attended OpenFOAM Workshop in Guimarães and you lived through this in person, you were given the links to these videos, so links to all the course materials. So thank you very much if you made it through all the videos up to here, and I hope that this piece of code might be useful to you. Of course, without any warranty, but we would be very glad for your feedback and your inputs. So thank you, and see you sometimes in the community. Bye.